Well, folks, this morning and actually all through the day, we've been hearing about trends in the energy markets, moving away from fossil fuels, moving towards electrification. This morning we talked about that. We talked about, excuse me, heat pumps and how heat pumps can come in. What I want to do this afternoon is show you some of the nuts and bolts and how do you implement systems that are operating at low water temperatures that are conducive to achieving good performance with heat pumps. So we're going to start off with low temperature distribution systems. For years, as we've been working with modulating condensing boilers, and as you've heard other speakers talk about today, lower water temperatures allow boilers to operate at higher efficiency. And it's the same story with heat pumps, whether it's an air-to-water heat pump or a geothermal water-to-water heat pump. So what are some options that are out there? Well, I'm going to show you that, but just a quick graph here in the upper left. Let's see, I think I can point to it. A typical ModCon boiler performance curve. I think Jeff had this curve up earlier. When you get below roughly about 130 degrees Fahrenheit, that efficiency starts to really climb quickly because you're starting to condense the water vapor that was produced as part of the combustion process. And again, to achieve that 90+% efficiency, you need to marry that modulating condensing boiler with a low temperature system. Over on the right here, it's the same story with a water-to-water heat pump. The lower the water temperature is, the higher the coefficient of performance is going to be. Solar thermal, I kind of cut my teeth in this industry over 40 years ago doing solar thermal. There's still a little bit of that around. Photovoltaics has kind of been the 800-pound gorilla in the room, so to speak. But solar thermal, solar collectors are the performance is very dependent on the fluid temperature you operate it at. And again, lower water temperatures, better performance. And finally, the air-to-water heat pumps, same story. So what we're talking about with low temperature distribution systems isn't just about heat pumps. It's really, in general, about all high-efficiency heat sources we have now, and again, the future-proof issue, looking forward, what will those heat sources be 20, 25 years plus from now? I don't know the answer, but my bet is that they will operate at higher efficiencies based on lower water temperatures. And we want to go to a slide here that this morning I mentioned this point. This is not a standard in the US or Canada. It is not a code that I'm aware of anywhere, but I think it's a practical number to think about, and that is when you design any type of hydronic heating system, that at design load conditions, that system can deliver design load output using a water temperature no higher than 120 degrees Fahrenheit. That puts it within the realm of most current generation heat pumps. It certainly puts it within the realm of boilers, solar thermal collectors, perhaps even other types of heat sources like electric thermal storage systems where we may charge up a tank using off-peak electrical energy. Yes, we can get that tank up to maybe 180, 190 degrees by the end of the charging cycle, but we want to be able to drain as much energy out of that tank and still maintain comfort in the building. So the lower the temperature the distribution system can operate at, the greater the delta T on the tank can be. So what's out there, okay? I've made a kind of a bar graph here of just what are traditional water temperature design ranges for different types of heat emitters. And of course, if I start kind of at the top there, traditional cast iron baseboard, traditional fin tube. Remember, we're going back to the 1930s with fin tube baseboard, and even before that with cast iron. Fuel was cheap. Efficiency really wasn't a driving factor in the market. The higher the water temperature, the smaller the emitter could be, and of course, the lower the cost would be. So higher water temperatures were very much the norm, kind of in those early 20th century systems. Fan coils, again, you can operate a fan coil at fairly high temperatures because you can reduce the size of the coil, or you can kind of move down towards lower temperatures. I'm showing here not really below about 120. That's more from a comfort standpoint. One of the things you want to be careful with low water temperatures and fan coils, besides just what their capacity output is, you want to be careful you aren't creating drafts in a space. You want to diffuse that air very carefully into the space, let it mix. You don't want to use, for example, 100-degree water through a coil and a fan coil and blow it directly at somebody. It's going to generate a complaint. Panel radiators, again, can span quite a range. The definite trend with panel radiators, if you watch the European market, for example, and I'll show you an example of it here, what I call fan-assisted panel rads. Now, we don't see many of these yet in the market. I think there were a couple entries in the market. I'm not sure what's out there. I think there's at least one manufacturer that has this concept. But if you've never seen it before, about halfway down on that panel radiator, you see there's a rack of very small little fans. These fans are like the fans you have in a desktop computer. They run on about 1.5 watts each at full speed. And those fans are in there to bring up the convective output of the radiator at low water temperatures. And they are specifically, that radiator system is specifically built to be compatible with heat pumps. The radiator manufacturers understand where the market is going. They want low temperature capability. And you can see that extends the range downwards. Some of these systems can operate down to water temperatures, even under design load, if they're sized correctly, about 95-degree water, 95-degree Fahrenheit water. So if you look at that blue box on the left, that's the range up to about 120 degrees. And you see, you've got options there. You've got several different radiant panel options, floor heating, wall heating, ceiling heating, as well as options with panel radiators, and if you're careful, with some fan coils. You know, oftentimes I'll hear somebody say, well, you know, floor heating is all low temperature. Well, yes, it can be. Be careful about doing things like what I call plateless staple up. Now, I'm not going to ask for a show of hands of who does plateless staple up, but you won't find that in other markets. You won't find that in Europe. They understand those aluminum fins are important to transfer heat laterally away from the tube. Systems like that, to get reasonable outputs, need pretty high water temperatures. And that's floor heating, but it's not really floor heating that's compatible with where we're going with energy sources. Okay, now slab-on-grade floor heating. This can give you low water temperature, okay? The downside of this is the high thermal mass. You don't really want to do this in a building that has very low heating loads and is subject to unpredictable internal gains, okay? Think about gains from windows, sunlight, or people. The problem is it's actually hard to stop the emission from the floor. If you've had a cold night, your system's got that floor nice and warm, the sun comes through the window, the load coefficient on those buildings is so low that literally within half an hour you'll be overheating the building. So you have to be careful about using high mass slabs in low load buildings when you have unpredictable internal heat gains. If it's something like a warehouse where you really don't have those gains, this can work very well for you. Okay, and of course, do a good job with your underside insulation and minimize the R value of floor coverings. Both of those will help bring that water temperature down. I've got a graph there that just, you know, I use that graph a lot. It just gives me an idea of what the output is with either 6-inch or 12-inch tube spacing and different finished floor resistance values. So that's one option. But I asked the question, is radiant floor heating always the answer? And I've had people say that's all they want to do is radiant floor heating. And of course, they're looking at ads like this. This is how radiant floor heating has been promoted over the years, what I call the barefoot-friendly floor effect, you know, the baby on the floor or whatever. You have to be careful about this. We talked about it a little bit this morning. In a low-load building, the floors really aren't going to get very warm. They don't have to get very warm in order to satisfy, let's say, a room thermostat setting of 70 degrees Fahrenheit, okay? And I'll actually show you, let's do a quick example on it, put some numbers to it. Imagine you've got a 2,000 square foot house that has a design load of 18,000 BTUs per hour, and that's very attainable today. And based on where codes are going, not only is it attainable, it's becoming more and more mandatable, I guess, if that's a word. you're going to see these energy requirements tighten. I know in the States we've seen it year after year. Codes will tighten up on what's allowed. So just to make it simple, let's assume 90% of the floor area of that 2,000 square foot building, 1,800 square feet, is heating. The other 10% might be stairwells or areas under kitchen cabinets where we don't have tubing in the floor. So we do a quick calculation. We've got to provide 18,000 BTUs per hour. We've got 1,800 square feet to deliver it. So we need to provide 10 BTUs per hour per square foot at design. So how warm does the floor have to get? Well, there's a simple little formula that is relevant to radiant floor heating. And just to put some numbers into that formula, if we're trying to do 10 BTUs per square foot per hour, that would be the Q in that formula, divided by 2, 5, plus the room temperature. Let's say the room temperature was 68. That means the floor surface only has to be 73 degrees Fahrenheit, okay? Not that often cited 85 degree Fahrenheit that was more typical under design conditions in buildings that had 3 times the design heating load, okay? And again, I want to stress, it's not that the floor heating won't work, it will. Just don't overpromise your clients that you're going to have those warm, toasty floors. The floors will still be warmer than they would be with pure convective heating, but they may not be as warm as what that client might have experienced in an older building that had floor heating in it, okay? Now, thermal mass, here's pictures of different types of heat emitters that we could tie into the system. We've got a 4-inch slab there, cast iron radiators, what I call above floor tube and plate down here, radiant ceilings, utility style panel radiators, and even these fan assisted panel radiators. So what I did, just to make a apples to apples comparison, I just calculated out how many square feet or how many pounds of heat emitter of these different types would be required to deliver 1,000 BTUs per hour using an average water temperature of 110 degrees in a room that's supposed to maintain 70 degrees, all right? It just looks at how much emitter is necessary to this kind of arbitrary 1,000 BTUs per hour. And if you look at the bar graph there, I'm sure it's not a surprise, the heated slab has much, much higher thermal mass than most of the alternatives, followed by the cast iron radiators, and then as you work your way down to this fan-assisted panel radiator, the fan-assisted panel radiator has less than 1% of the thermal mass of that heated slab. If you have a low-load building and it's going to be subject to internal gains, the low thermal mass heat emitters are better. They're going to be able to track that load better than a high thermal mass heat emitter will, okay? So keep that in mind. Radiant ceilings. How many here have done a radiant ceiling? Anybody? A few of you have, okay. Again, I look at radiant ceilings. We've done several projects with radiant ceilings. It's a very underutilized strategy. And quite honestly, one of the things that I think will come into our market soon, even at residential scale, is radiant cooling. Right now, there's a commercial market for it. The big thing is, of course, you can't run water or you can't run surfaces below dew point, otherwise you're going to get condensation. But radiant ceilings are ideal for chilled water cooling, provided you've got proper dew point control on the chilled water. They're better than a cold floor or a cool floor. So a radiant ceiling can do a really good job in heating. And, again, some people, customers, clients think, well, how does the heat get down from the ceiling? Well, it's radiant heat. It's light. It's just like that, these lights on the ceiling. It shines down on objects. So, again, I look at a system here that's using aluminum plates, 8-inch tube spacing, good backside insulation. There's a construction detail shown for it, and that equation over there is the performance. And I'll give you a quick set of numbers. If we had a 110 degree average water temperature, again, well within what we could do with a heat pump or a ModCon boiler, we have a 70 degree room. So you look at the difference over here between the water temperature and the room temperature, that would be 40 times 0.7 28 BTUs per hour per square foot. That's a pretty good output from any emitter when you're working with an average water temperature of 110 degrees. And think about this, if we could get 28 BTUs per hour per square foot from a radiant ceiling, but our design heating load in the building was only 10 BTUs per hour per square foot, the implication is 1 square foot of ceiling would cover the load of 2.8 square feet of floor area. So we don't necessarily have to do the entire ceiling with radiant panel construction. It might be part of the ceiling, okay? So again, that's a cost-saving option for you. And you see the infrared photograph over there on the far right. That's actually a radiant ceiling we did, over 20 years ago with the aluminum plates. And can anybody tell me which way the water is flowing across that ceiling? It's actually, that was taken about maybe 30 minutes after I turned the zone on. It's going from left to right. How'd you know that? Yeah, you can see that red, right? That red is showing you what those aluminum plates are doing. They're diffusing that heat away from the tube, spreading it out across that drywall surface, giving you a better approximation of a uniform radiant surface. Okay, it's still not perfect, but it's better than not having those plates there. So this is an option that, again, I would suggest you take a look at this in projects, especially projects where the client, they want some type of thick carpet. I guess shag carpet's out, right? I know it's out in the US. I assume it's out up here too, right? Anybody remember shag carpet? Yeah, that was my job as a kid. I had to rake my parents' orange shade carpet with a plastic rake. But any kind of high-resistance floor covering can more or less rule out the use of floor heating if you're also trying to be compatible with low water temperatures. So radiant ceilings are an option for you. Take the same construction, turn it 90 degrees, and create radiant walls. Here's a radiant wall going into a Cape Cod-style interior, attic trusses, a 4-foot-high knee wall. It's exactly the same construction as the ceiling system, 8-inch tube spacing, 5-inch, 6-inch wide aluminum plates. And again, it gives you actually a little higher output than the ceiling does. And that's because there's a little more convection on a vertical surface transferring heat compared to a horizontal surface at a ceiling. And what do you suppose the photo of the stairwell is there? Any ideas? I don't see any radiators on it. Well, that stairwell actually is a radiant wall. This construction was integrated into it, and of course, you can't see that, but it shows you opportunities within buildings to integrate radiant panels. And remember, the more surface area that you create on your heat emitters, even if it's a mix of heat emitters, you're mixing maybe some radiant floor heating, some panel radiators, for example, the more surface area you have, the lower the water temperature is going to be, and the better the performance of those heat sources. Okay. We talked about thermal mass on heat emitters. One of the things that's very impressive with panel radiators is how quickly they warm up. And I want to show you, this is a sequence of 4 thermal images. I took these. That represents about 4 minutes from when I opened a thermostatic valve on a radiator and just took, like each minute, I took a picture of what the surface of the radiator looked like. And it's pretty interesting to me. You can see how that hot water is moving across the upper manifold of the radiator and then moving downward through the channels on the face of the radiator. But after 4 minutes, it's not quite steady state, but it's pretty darn close to steady state over there. So again, low mass emitters like panel radiators allow you to not only bring the heat on quickly in a space, especially the radiant component of that heat delivery, they also allow you to turn that heat rate off when you get an internal gain. So it's the ability to track these rapidly changing load conditions that low thermal mass is better. This is just a picture of this is a European product, Vogel and Newt. You can look them up online. But it's an example of one of those fan-assisted panel radiators that actually has a little circuit board in it. Those fans will vary their speed as the room conditions change. It still has a thermostatic valve on it, so it uses that type of zoning. But I think you will see more offerings in North America pretty soon on this because, again, these are ways to evolve a basic panel radiator design forward to give you better compatibility with low temperature heat sources like heat pumps. Okay, what about retrofitting existing hydronic systems in transitioning buildings over to electric, okay? Now, questions that come up a lot about this, and I know other people have mentioned this today. Can the utility grids handle rapid and extensive shift from all fossil fuels to electricity? It's questionable. And, you know, I'm not a utility grid expert, but I still do question when I look at not only the press for electrification in our HVAC systems, but also electric vehicles. And both of those happening simultaneously. And the question is, can the grid keep up with that? We'll probably find out. I think there will be some strain. Anybody follow what happened in California last week with their heat wave? You know, the Nest thermostats were limiting cooling to about 82 or 83 degrees. The utility was controlling the Nest thermostat. And people that probably had signed on some agreement about allowing the utility to control the thermostat, they were still upset that they were, you know, not able to get their spaces down to normal temperatures. But they had to do it. They had to shed load. And we're seeing other utilities shedding load in the case of forest fire potential. So it's already, the strain on the grid is already starting to show up, and I think, especially based on these regulations we've been talking about today, I think we're going to see more and more instances of not all-out failure of the grid, but we're going to see times when certain areas in the grid are going to experience some strain. And another question, should all existing hydronic heat sources operating on fossil fuel be immediately scrapped and replaced by a heat pump? I don't think they should. I think there's a lot of synergy in keeping, the basic concept is you shift the vast majority of your energy supply to the heat pump, but you keep the backup, you keep the boiler in there for several reasons, okay? I put this graph in just to show you what's happening. Again, I'm from New York State. For years, New York State has been a summer peaking utility situation. Basically, air conditioning down by the city is a huge, huge, you know, megawatt type load. But predictions are that with the growth of heat pumps, that the New York State electric system as a whole will shift to a winter peaking utility in about 10 years. And you can see how that orange curve is kind of gaining on the blue curve there. So winter peaking is going to, again, be what the utilities are going to deal with. Whether or not they have the capability and how quickly they can bring on additional distribution remains to be seen. Okay. Now, I put down hydronics technology can enable a rational transition. I'm not against the eventual and rational transition out of greenhouse gas producing fuels into energy systems that produce less of that effect. But it has to be rational, okay? So I put down, don't write off an existing, or for that matter, a new construction, a boiler in combination with, let's say, an air-to-water heat pump. In a really quick schematic, this happens to be a split system air-to-water heat pump. So you have an outdoor unit, you have refrigerant line sets that come into an indoor cabinet, and you'll see that's piped in with a circulator. There's a check valve in that portion of the circuit. And then next to it, I've got a conventional boiler. Could be a cast iron boiler, steel boiler. One of the details you see on that is what I call an anti-condensation valve. Another thing to keep in mind is that we have, you know, thousands, probably tens of thousands of cast iron boilers in the market. And they have operated for years, maybe on baseboard systems where the water temperatures have been relatively high, 160, 180, maybe even a little higher. They're above the dew point of the flue gases, the vast majority of their operating hours. Okay, so they don't experience what I refer to as sustained flue gas condensation. You might get a little intermittent flue gas condensation from a cold start, but they aren't operating hour after hour in a condensing mode of operation. So if you're going to add, for example, insulation to a building, do a deep energy retrofit, you're bringing the load down substantially. You're also bringing down the water temperature that you need to operate that system at. Basically, water temperature comes down in proportion to load reduction, okay? Quick numbers that I can happen to remember. Imagine a building, an original building, 100,000 BTUs per hour design load. Let's say you add insulation, you improve the windows, you air seal it, whatever you do, you bring the load down to 70,000. That would bring your water temperature from 180 at design, 180 Fahrenheit, down to 147 degrees. So you get a substantial reduction in water temperature. Okay. Now, if you add heat emitters, you expand the distribution system, you add more surface area, that will bring the water temperature even lower. Here's the danger. If you keep that conventional boiler in there and you don't do something like an anti-condensation detail on it, you're taking a boiler that perhaps for years has operated well above dew point without problems, and all of a sudden you're creating a problem. The problem is you're going to run that boiler at conditions, low water temperature conditions, that will allow sustained flue gas condensation. And I've seen this happen. And it will destroy a galvanized flue in a matter of months. And eventually it will corrode the boiler as well. So you can keep that conventional boiler, assuming it has service life left to it. You simply have to add an anti-condensation valve. And what that does, on cold conditions, it will recirculate the water coming out of the boiler outlet right back into the inlet. It brings the boiler temperature up quickly above dew point, and then it allows that energy to flow out to the system. So basically, the heat pump and the boiler are in parallel. So a control system could call either one to operate. Typically, you would give priority to the heat pump for the majority of the load, but if there are conditions where the heat pump can't keep up with the load, it could be as simple as a two-stage water temperature control, looking at a temperature in a buffer tank. It could be a two-stage thermostat, but we have control methods that would allow that boiler to come on either as a supplemental heat source, or if we had an outright failure of the heat pump, it could be the sole backup heat source for the building. I mean, it's there, it's been working, it's been heating the building, it has service life left to it. Let's work around it rather than tear it out. I hope that makes sense, but believe me, I have talked to people that have such animosity towards fossil fuel. They immediately want to take everything that operates on fossil fuel and just tear it out of their house. And I try to bring them back to, well, eventually, yes, you can remove that boiler, but have you thought about using it as backup, supplemental heat, and so forth? Okay, so again, supplemental heat, extreme weather with an air-to-water heat pump. Yeah, I mean, we get temperatures where I live, and I'm sure you do up here too, minus 20 degrees Fahrenheit. And under those conditions, that heat pump is really struggling. Even current generation, low ambient, vapor-injected compressor-type heat pumps, their capacity is pretty low under those conditions, so we need supplemental heat. Well, the boiler's there. We can use it for supplemental heat. If the heat pump is down, we have full backup heat. Now, this is one to think about. Backup heat powered from a small generator. I could run an oil burner on a cast iron boiler on about 400 watts from a little Honda-type generator, all right? If I have a heat pump or if I have electric resistance heat, I need a much larger generator. So this goes back to that word I used this morning, resiliency. The resiliency is that a small, affordable generator could keep the heat on in a building with a boiler, a fuel oil boiler or gas boiler, using much, much less power than what would be required if you're entirely an electric system, okay? And then again, from a utility standpoint, the peak load situations that these utilities are facing, what we call a dual fuel concept. Again, heat pump, majority of the energy, the boiler, whether it's new or existing, as the supplemental. So, okay, here's a typical baseboard system. We've got maybe an oil-fired cast iron boiler. We've got a series loop of baseboard. It was designed around high water temperatures. The question is, can a heat pump tie into a system like this? Could I, for example, simply put an air-to-water heat pump in parallel with that boiler and just keep that distribution the same as it is? Well, we've done some modeling on that, and it's kind of interesting what happens. This graph that I've got up there is something that I'm sure many of you have seen. It's called bin temperature data. Simply, what it does, it takes a location. We could take Toronto, and I'm sure it's probably done for many of the suburbs around Toronto at this point. But this graph is for Syracuse. And for Syracuse, out of the entire year, we simply take the outdoor temperature and we put it into 5-degree wide bins. How many hours out of the year was the outside temperature between, let's say, 20 and 25 degrees Fahrenheit? Well, I could go to the graph and look that up. And what you see there is that if you look at the really cold temperatures over here, yes, in theory, in Syracuse, it could get to minus 20. It might not happen every year, and when it does, it might only happen for an hour or two. So it's the amount of energy as a percent of the total energy use over the season, even under that extremely cold outdoor temperature, is very small, all right? And yet, as you start to move from left to right on this graph, you can see what's happening. You spend a lot of time in a heating season within that temperature range, that outdoor temperature range. So how does that reflect back to the distribution system? There are substantial periods of time when an unmodified high-temperature baseboard system could still operate from a heat pump and provide enough heat. It would use outdoor reset control on the water temperature. It's not going to cut it when it's, very cold. Simply, you have to look at how the capacity of the heat pump drops versus what the load does. The load's going to increase. But the models that we use, and I'll show you some software, and again, this is an Excel spreadsheet, but this is a project we did for New York State Energy Research and Development Authority. They wanted to know how will a heat pump work in different areas of New York State. And there's a lot of climate diversity in New York State. So what we did is we modeled buildings from Plattsburgh, New York, which is right below the Canadian border, 8,000 degree Fahrenheit days per year, all the way down to Brooklyn, okay? And of course, substantial differences in climate there. And we found some interesting things, and I'll show you one of the results for Plattsburgh, because again, Plattsburgh's a pretty cold climate. I mentioned 8,000 degree days. We modeled a building that has a 36,000 BTU per hour design load at -9 Fahrenheit, which is design load conditions in Plattsburgh. We're going to maintain 70 degrees inside. We're using a nominal 4-ton rated, that's 48,000 BTU per hour, vapor injected, single stage compressor heat pump, okay? We're assuming an average internal gain of about 2 kW. Lights, computers, there's a lot of stuff plugged in houses today that gives you this background internal heat gain. So we assume that averaged about 2 kilowatts. Domestic water load. Now, we model systems with and without domestic water usage. But when domestic water was present, the load was 60 gallons a day, heated from 50 to 120 Fahrenheit. And what we did is we changed the supply temperature for the heating system. We started at 100 degrees and we went all the way up to 180. We wanted to see the effect of design load water temperature of the hydronic system on heat pump performance. And we assumed during the heating season full outdoor reset of water temperature. In other words, the heat pump on a part load day isn't going all the way up to a certain temperature, all right, that we would need at design conditions. That is going to improve seasonal performance. The other thing, and I guess I didn't put it on here, we did not allow the heat pump to supply any load that required more than 130 degree Fahrenheit water temperature. Many of the air-to-water units that are out there now can do 130. Some can actually do higher. Now, again, performance does go down in terms of COP, but they are capable of sustaining 130 degrees, even at, say, 0 degrees outside. In our simulations, we did not allow any heat pump energy input when we were requiring a water temperature of 130. So let's start over on the left. That's the supply water temperature required at design load. In the red column there, seasonal average coefficient of performance when there's no domestic water. Again, this is Plattsburgh, this is cold. Ranging from a low of, at the high water temperature requirement, unmodified baseboard system, we'd have a COP, seasonal average COP of about 2.6, and we were still covering about 91% of the load of that house. Now, Don't generalize this to every house. This was a specific house in a specific climate with a specific heat pump. But representative of the construction that is out there now, especially built to current codes, we were covering, in round numbers, 90% of that seasonal energy. And you can see as the water temperatures go down, starting from the bottom of that chart and going up, we're covering, in 3 cases, 100% of the load. Now, that's a 4-ton heat pump in a building with a nominal 3-ton design load. So that heat pump was, somebody might say, well, it was oversized for the load. Well, with a buffer tank, you can do things like that, especially today with inverter compressors. You can, you know, there's not that penalty that used to be associated with oversizing air source heat pumps, where they were grossly oversized in cooling. Now, when we added the domestic water load into it, you can see the seasonal COPs improved slightly. And part of that is because the simulation also went through the summer months. We're using the air-to-water heat pump for domestic water heating in the summer. And we did not, again, we put temperature restrictions on what that heat pump could do. We would not let the water temperature that the heat pump operated at go above 130 degrees. And again, you can see our percentages of our total load, and that should actually say space heating plus domestic hot water. We're still ranging from about 89 to almost 96%. So it shows that you can displace a significant part of a seasonal space heating energy requirement even with an unmodified distribution system, a legacy system that is designed around high water temperatures. That being said, I would still encourage you, if you're evaluating a system, to look at possibilities to add heat emitters to a system. Anything that you can do, even if it's done over time, that adds more heat emitters to the system, brings water temperature down, and ultimately would improve performance. But these numbers were encouraging. These numbers, they're not quite as good as what you'd get with a geothermal heat pump, but again, substantial reduction in cost for an air-to-water heat pump relative to a typical residential geothermal installation, simply the absence of the earth loop, okay? Okay. This is just a graph. That shows, again, the effect in those 3 climate locations, Albany, Brooklyn, and Plattsburgh. We were talking about the green curve here. It shows that it was kind of interesting. If you look at the difference between 100 and 120 degree water temperature at design load, the curves are relatively flat. That tells me that that isn't very sensitive. Now, the lower the water temperature, the better, but the change is small. But once we go over roughly 120, you can see those curves start to steepen, and they really start to dive down as we get into these higher water temperatures. So it's a trade-off. If you're willing to either improve the thermal envelope of the building, add heat emitters to the system, or some combination. And in New York State, there's all kinds of incentive programs now, especially for low and moderate income properties, to add insulation, even subsidizing heat pump installation. So if you're willing to do that, you're going to improve the seasonal COP of the heat pump, okay? So we were seeing life cycle costs that were comparable to what you'd see with a geothermal system with this. And by that, I mean, if we look at over a period of, let's say, 15 years, what is our total operating and owning cost, and we're comparing, well, a higher price for the air-to-water system versus a standard air-to-air system, a ducted air-to-air system, we were still seeing comparable life cycle costs. So it is a simulation. This is not experimental data, but the results were encouraging. You know, if we were seeing COPs of 1.4, 1.5, something like that, you know, it's not much better than what Tom mentioned with an electric resistance heat. COP is 1. But we're seeing COPs that are starting to approach what we're getting with geo and doing it at substantially lower cost. That's just heating, percent of heating and domestic hot water load. I'm not sure why that red curve does that little blip up there. It could be something to do with climate data. But again, you can see the low water temperatures are giving you higher percentages of the total space heating energy, and it starts to drop off as we go into those higher water temperatures. Okay, what about domestic water heating? Now, one approach that comes up quite a bit is to say, well, I'm going to put an air source heat pump in. It could be ductless mini split, it could be central air to air, and that'll take care of my space heating and it'll take care of cooling, but for domestic water, I'm going to put in a heat pump water heater. Anybody here doing a combination like that? Air to air heat pump, maybe ductless mini split, and then heat pump water heater, okay? Well, I looked at this. You know, here's obviously a ductless mini split, and this is what we're going to do for domestic water. That's a heat pump water heater, okay? So here's what it looks like thermodynamically. We've got one heat pump on the left here. I call it heat pump COP1, okay? It has some performance value to it under nominal conditions. And of course, we are absorbing free heat from outside air. We're combining it with electrical energy, and we're sending that energy into the building envelope. That's what that little house shape represents. Now, within the thermal envelope, we have the heat pump water heater. And I'm going to tell you the assumption that I put in here, which is partially valid and partially invalid. The assumption is all the energy that that heat pump water heater gathers was put into the thermal envelope by heat pump number one there, okay? So we're taking away things like internal gain, okay? We're separating this from the standpoint where maybe in some type of a commercial environment, you might have surplus heat in a certain area that you're trying to get rid of anyway. That's a great solution to put a heat pump water heater in if you have a domestic water load. But in this situation, we're looking at heat pump number one on the left puts the energy in the thermal envelope, and then heat pump number two absorbs some of that energy, combines it with more electricity, and puts that into your domestic water. And it's kind of an interesting thing, because this is what the math ends up looking like, and it's pretty ugly, isn't it? But this is actually a net COP. And by net COP, I mean, what is the ratio of the heat actually delivered to the domestic hot water divided by the electrical energy input? And to give you a quick summary, I took two heat pumps. The space heating heat pump had a COP of 4, and the heat pump water heater had a COP of 3, and I processed them through that, and the net COP is about 2.0. So what does it mean? It means that the actual beneficial effect of a heat pump as a water heating device is not as good as what that rated COP is, because it's taking energy that really isn't free energy. It's taking energy that you paid the other heat pump to put into that envelope. That's why those numbers work out the way they do. So I would contend that, again, using a low ambient air-to-water heat pump on an annual basis and bringing the domestic water load into the picture is a better solution than using something like a ductless mini split along with a heat pump water heater. You're going to get higher average seasonal COPs. You're going to be able to heat the water with a heat pump, but do it more efficiently than that combination of, let's say, a ductless mini split system with a heat pump water heater, okay? So let's take a look at control strategies. Here's a schematic. This is what's called a monoblock or self-contained air-to-water heat pump on the left. This system would have glycol in it to protect the outdoor unit. And we're coming in, we're going to a diverter valve right here. And in the heating mode, we're going to send water over to, I'm showing what I refer to as a reverse indirect tank. It's a tank that has water in the shell and then suspended coils. Domestic water goes through the coils, not the shell. So the nice thing about a reverse indirect, it can serve as not only your water heating device, it also can serve as a buffer tank for your space heating loads. And over on the far right, you see I've got a manifold, I've got panel radiators, a variable speed circulator. I think that is an ideal, simple, repeatable, reliable distribution system. But we could definitely have situations where the load might be 1,000 BTUs per hour from one panel radiator, and you've got a heat pump that simply can't go down that low. You need some buffering mass in the system. So that's what that tank does. Now, the red note there, number one, says during heating season, the buffer tank temperature is maintained based on outdoor reset. We're doing that to bring up the annual COP of the heat pump. The downside of using outdoor reset in a system like this is that under partial load conditions, our domestic water is not fully heated. Assuming you want water at, let's say, 115, 120 degrees. If we're only going to heat the tank up to 95 degrees because that's warm enough on an April morning to supply the space heating load, and we want domestic water at 120, we've got to boost it. So you'll see, I'm just showing a conventional, maybe a 30-gallon electric water heater. There could be other options. It could be a tankless electric water heater. It could be really anything that can give you a boost on the domestic water. I'm also showing in parallel with it an electric boiler. And this is assuming now you want to go to a full electric system, okay? So the electric boiler would operate, again, as supplemental heat generation to the heat pump. It would also operate, if it needed to, as either partial or full backup. It would depend on how you size that electric boiler. And by the way, when you size up an electric boiler, if you're going to do whole house space heating with it, make sure you include the cost of the electrical cable and fittings back to the breaker panel, because those costs are very high today, and make sure you've got at least a 200 amp breaker panel. All right? You're going to need it. They draw a lot of power. Now, the other thing you see at the bottom of that schematic is a chill water air handler. And the diverter valve simply determines which way does the output from that heat pump go. In a cooling mode, the diverter valve would route that down through the coil in the air handler. And it's important to understand, if you're going to go direct, notice that the buffer tank is not participating in the chill water cooling. All right? We're not buffering chilled water in this system. So we're counting on the heat pump capacity being matched to the coil capacity in that air handler. Now, an inverter compressor heat pump can do that. It can vary its speed. If you want it to track, let's say, 45-degree chilled water outlet temperature, as the air handler load changes, it can modulate the compressor and do that. If it's an on-off compressor, you have to make sure that the coil capacity in that air handler is matched. Okay? It's not an ideal scenario when you have an on-off compressor. It is better suited to an inverter compressor type heat pump where, again, the heat pump can adjust its output so that it keeps up with the coil, and it simply maintains a certain chill water temperature to the coil. Now, you might be thinking, well, why don't you just put the chill water into another buffer tank, and then you wouldn't have to worry about that? Well, you could do that. It adds quite a bit of cost. The other thing about this system is, in the summer, this heat pump can basically toggle when necessary between cooling and domestic water heating. Typically, space cooling would be the priority load. So if it's cooling, if we've got a call for cooling, we're going to temporarily interrupt energy input, heat input to that indirect tank, but we're going to limit that. We might limit it based on time, okay? Maybe we're going to, I'm sorry, I'm backwards. The priority load is domestic hot water. The reason it's domestic hot water is that you can satisfy that load very quickly in the summer. You can bring a 119-gallon tank up 25, 30 degrees, and you could do the math, 10 minutes, maybe 15 minutes. When it's 75 degrees outside, you're going to recover it quickly. So during that time, you could keep the blower on in the air handler. You could still circulate air in the building. When you come out of domestic water heating and you go back into chill water cooling, you've got to be careful. Anybody know what could happen? Think about it. The heat pump's sitting there running at maybe 125-degree water temperature, and all of a sudden you just move that diverter valve. What's immediately going to flow to your chilled water coil? 125-degree water. And that's not hard to get around. You simply would use some kind of a temperature set point control that doesn't allow the blower to operate until the chill water temperature has come back down. And that might only take a couple minutes, okay? So, again, control strategy. We don't want to send a slug of hot water into a chilled water air handler and have the occupants experience that real blast of warm air, and then it eventually chills down. So that's part of the strategy. During non-heating season, the buffer tank temperature, we're going to go away from outdoor reset. We're going up to a higher set point temperature range, in the range of 120 to 130. What does that buy you? Well, first of all, it buys you pretty much 100% capability on domestic hot water. Assuming your water temperature, your delivery water temperature is 115, 120 degrees. If you're trying to do 140, 150 degree water for whatever reason, industrial process or whatever, again, you're not going to get a heat pump right now, other than maybe some CO2 heat pumps can go into that temperature range, but most of the R410A heat pumps, 130 is a good practical upper limit. But during the summer, we have much warmer ambient temperatures, okay? The COPs are going to be really good, even if we're doing 120, 130 degree water. So we are getting a higher percentage of our domestic hot water load in the summer simply because we have higher ambience and we're not taking a penalty on our coefficient of performance. During cooling season, a call for cooling, I've got that backwards again. It says call for cooling takes priority to call for domestic. You could do it either way, quite honestly, but actually what I just described to you was domestic hot water as the priority load. Temperature-based time delay on air handler blower startup to allow fluid to chill down before you turn on, restart the blower for cooling. So again, you can start to see some new control concepts working in based on the presence of chill water in the system. Okay, ventilation. Here's a system. I've taken that same basic system. It's a monoblock heat pump. It's coming into a diverter valve. We've got a reverse indirect serving as the buffer tank and as our water heating. We've got a highly zoned distribution system. I'm showing some panel rads. It might even have some radiant panel circuits with thermostatic valves. This is one of the nice things about a home run system design. You can mix heat emitters. Set up a manifold. Half-inch PEX is typical, or PEX aluminum PEX, or PERT. The tubing all is well within the temperature pressure of what we need. You could go out to panel rads, you could go out to towel warmers, you could go out to radiant wall panels, you could go out to floor heating, okay? And it's all, as long as you design all those heat emitters around the same water temperature. You know, I can't run a panel radiator at 120 here and run a floor circuit at 105 over here without putting mixing valves in, and that would complicate the home run system. The other thing that you'll see over on the far right side of that manifold, and I'm a big believer in promoting this, I always like to see at least one extra connection pair on a manifold station. So 5 years from now, maybe they might say, well, I want to add a towel warmer to this bathroom. You got the connections, all you've got to do is isolate the manifold, bring in the PEX to the towel warmer, connect it, and you're back in business. If you don't put those extra connections in, you can still do the work, but it's more work. You've got to drain the system, maybe expand the manifold or whatever, tie into the piping. So you can sell the idea of at least one extra connection set, sometimes even two. I actually had in a house we did a couple years ago for my daughter, I tried to talk her into a towel warmer in both the master bathroom and the regular bathroom. No, we're going to just do it in the master bathroom. Guess what she asked me for last year? Can we do a towel warmer in that other bathroom? And we do have extra connections to do that. So it's again, it's kind of a little upsell. It's not very expensive to do it. You simply cap off those extra connections until you need them. But again, think future-proof. You can sell it, okay? Here's I didn't explain the bottom part of the system. You'll see the air handler down there. The air handler is for single zone cooling. You could do motorized dampers on some of your runouts if you wanted some zoning. But I tend to like single zone cooling. And right above the air handler coil, you see another diverter valve. Now, in cooling mode, that diverter valve takes chill water from the heat pump and runs it through the coil, just as we talked about. But in the winter, if you look to the left, and I'll see if I can point to it here, here's our HRV. And I've tied the HRV into the duct system here. What we're going to do is introduce fresh air. It's come through the HRV. It's been warmed to some degree, depending on heat recovery efficiency of the HRV system. But again, on a very cold day, if we took air at -10 and we run it through a typical HRV with a 70% assumed heat recovery, we're coming out of the HRV at around 45, 46 degrees Fahrenheit. That's still relatively cool air. You'd have to be very careful how that's introduced into the space. Well, you got a tank full of warm water. You've got a circulator up there that is running basically 24/7 on a home run system. These pressure-regulated variable speed circulators, you can run them 24 hours a day in the wintertime. If all the radiator valves are closed, they drop down to around 9 or 10 watts, almost a trivial amount of power. When a radiator valve opens, they reawaken, they come out of sleep mode and basically speed up as necessary. So the circulator's running, waiting for TRVs to open up. Why not take another circuit from I'll see if I could trace it here, from right here. This could be a piece of 1/2-inch PEX, goes into the diverter valve, and what this is doing is it's going to allow some warm water to go through that coil as a ventilation air booster. So instead of 46-degree air coming out, we could bring that air up to, let's say, a room neutral temperature of 70 degrees. And the way that is being regulated is just a thermostatic valve. It's a radiator valve with a capillary tube, or I guess you say it capillary tube up here, right? It's one of the Canadian words I learned many years ago from Robert Bean, capillary tube. It's a capillary tube control that simply monitors that discharge air temperature. So when it needs a little heat input, it trickles some of that warm water from the buffer tank through that coil. It's another feature beyond what a standard HRV can do. It's a comfort-enhancing feature, okay? The other thing that we can do with ECM blower motors now, we can go from a nominal 400 CFM per ton speed mode in chill water cooling. We can drop that ECM, and some companies will change the programming in the blower for you. We can drop that down to about 150 CFM and perhaps even lower. So we can run that blower motor at a very reduced speed on a ventilation-only mode. And we're putting our fresh air in on the return side of the air handler, and we're simply not running the air handler at full speed just because we want to save some input power to the blower. You know, you could run at 1200 CFM and just inject the fresh air into it, but you don't really need that in a ventilation-only mode. And we're not trying to do space heating with the air handler. I want to point that out. We're only trying to bring the ventilation air up to a room-neutral temperature using some warm water from the buffer tank. So there again, that's what you can do with a hydronic system. You can't do that with other approaches. Okay. Real quick, I'm going to just run you through some example systems. It'll take maybe another 5 minutes. Again, monoblock heat pump, antifreeze in the entire system, reverse indirect. Again, we get preheating with the coils in the tank, and this time I drew in a tankless electric water heater as a booster or potentially as a backup if the heat pump was out of service or for whatever reason we aren't getting a temperature preheat in the tank. And then a variable speed pump, pressure-regulated pump, out to a home run distribution system, manifolds, and mix and match your heat emitters, panel rads, radiant panel circuits, towel warmers, okay? And again, it's representative. You know, I'm showing like 4 panel radiators. You could have a dozen panel radiators. You can scale this concept very easily. And you have a variety of products right here to look at for panel rads, for manifolds, for circulators, all of which could facilitate the concept here, okay? So reverse indirect provides year-round domestic hot water. Tankless water heater provides a boost if necessary. All right, here's another approach. Again, a monoblock air-to-water heat pump, antifreeze in the system. I've added the chill water air handler with a diverter valve that, again, routes the output of the heat pump either to the buffer tank or to the air handler. The buffer tank doesn't have coils in it this time. So how are we doing domestic water? Well, we're doing it with that external brazed plate heat exchanger. This is a detail that is used in Europe quite a bit, yet we don't see it used over here. And we've designed systems around this, and it works. It's a stainless steel brazed plate heat exchanger. I'm sure many of you worked with them. And it can be set up on a flow switch. So whenever a tap for hot water is open and the flow gets up to about 0.7 gallons per minute, that little switch will close. You can run the contacts from that switch right to one of your zone relays, so you aren't directly switching line voltage through it. And that simply turns on the circulator to the right side of the buffer tank right here. And that will bring hot water from the top of the buffer tank through that heat exchanger and talk about response time. You'll have water temperature almost at steady state in about 5 seconds. That is definitely faster than a gas-fired tankless water heater can bring you up to a set point temperature from a cold start. And if necessary, depending on the temperature in the buffer tank, you could run that to a booster if you want to. If your heat pump is maintaining that buffer tank warm enough to satisfy your domestic hot water load requirement, you wouldn't need the backup. When you size that heat exchanger, be generous. The guideline that I would suggest to you, you want the heat exchanger size so that the difference between the incoming water temperature from the buffer tank and the leaving water temperature, which would be your domestic hot water now, leaving the heat exchanger, no more than 5 degrees Fahrenheit. We call that the approach temperature difference on a heat exchanger. And even narrower is better, but the size of the heat exchanger will get large. But you don't want to go in there with a little 3 by 8 inch brick with 5 plates in it. It just doesn't have enough surface area. So there's online sizing software from many of the heat exchanger manufacturers that let you size that up correctly. Okay? And again, I've just drawn a distribution system over on the side. I'm trying to show a mix of panel rads with thermostatic heads on them, as well as radiant floor circuits, which are also controlled by thermostatic valves with capillary tubes going up to a wall-mounted adjustment. We did this actually in my daughter's house. We mixed panel rads and some floor heating circuits, and it works beautiful. Just make sure, again, you design and size your panel radiators and your floor circuits or whatever those heat emitters are. You want them all to operate at the same temperature. You can do reset of that temperature, but I can't size a radiator for 120 and a radiant floor for 100 and without putting some mixing in between there. Okay, we've talked about that. All right, what's this one now? Oh, this is a split system. I'm just changing the heat pump from a monoblock to a split system. This one would not require antifreeze in the system. You could still put antifreeze in if you want it for other reasons. But because it's only refrigerant going to the outdoor unit, we don't need to put antifreeze in. The buffer tank, again, no coils. It uses the external heat exchanger for domestic water. I'm assuming we're going to need a boost on domestic water. I'm showing a small electric resistance tank to do that. And then the space heating distribution system is the same thing. It's a home run with a variety of heat emitters in there. And again, that little variable speed circulator right here, basically turn it on in September and turn it off at the end of April. And let it go up and down in speed based on what the flow and what the flow requirements are in the distribution system. Okay. Monoblock, backup boiler. Maybe it was an existing boiler. Again, I'm putting that anti-condensation valve in there because I'm assuming my distribution system will operate at relatively low water temperatures, or could down the road. Remember, the more weatherization you do on a structure, the lower that water temperature requirement can be. So protecting that conventional boiler against sustained flue gas condensation is an important detail, and there's several products, and quite honestly, there's other methods to do that, but this is simple. It's a thermostatic mixing valve designed for that purpose. Domestic water is preheated by the coils in the tank and boosted by that tankless electric water heater. So hopefully you're seeing, a variety of solutions. Almost done. Here's a really simple application. I think this one is sometimes overlooked. No buffer tank, just a hydraulic separator between the monoblock system and a high mass single zone load. All right, we don't need a buffer tank if we've got 50 yards of concrete in a floor with tubing going through it. We've got a lot of thermal mass, but we gotta be careful. I stress single zone. If you take that 50 yards of concrete and chop it up into 10 little zones, now you're going to have a mismatch between what the heat pump can do and what the load requires. So think about things like shop buildings, metal shops, wood shops, fire stations, aircraft hangars, ambulance garages, highway garages. Okay, those are all potential applications for a system that's really simple. The hydraulic separator allows you to do constant circulation in the load side of the system, which is really good in a garage type facility. So you don't get those cold spots inside those overhead doors. keep the circulation moving, and yet the heat pump, all the heat pump's going to do is track a supply water temperature, which could be a set point or could be outdoor reset. And the hydraulic separator, again, it gives you the air separation, dirt separation, the magnetic separation that Jeff was talking about earlier, and we don't need to put the buffer tank in. So there's a definite niche in these commercial garage-type facilities where these heat pumps would fit in with relatively simple means. If you need more capacity and you don't have three-phase capability, you could use multiple air-to-water heat pumps just like you use multiple boilers. Stack them up, rig them into a common header system, individual circulators and check valves on each heat pump, feeds the hydraulic separator, and then the rest of the system is the same. And by the way, if you want to go to a client, like I just think about some of these metal fabrication shops, you know, the guys in there in the summer, it's 100 degrees in there, they're sweating, they don't have cooling, or maybe they got a window shaker or something like that. You got a heat pump. You can give them chill water cooling with an air handler. You go into a traditional building that has not had cooling and say, not only can we bring a heat pump in and bring your, you know, we're paying $5 a gallon for fuel oil, $5 US a gallon now for fuel oil. We can bring that cost down with a heat pump. We can go satisfy the regulation side of this, the decarbonization effect. And by the way, we can add cooling to your building. Would you like that? A lot of opportunity, okay? And a final thought, and I'm out of here. Well, I'm done up here. Low energy loss buildings. I think probably everybody would agree this is where we're at. This is where we're going to continue, where the market is at, okay? Modern hydronics technology, whether it's the circulators, you know, the panel rads, whatever, and heat pumps. The technology of bringing all this together is going to give you energy cost savings relative to where some prices are certainly right now. Superior comfort. This morning I said don't ever undersell comfort. It's still the main reason people buy hydronic systems. And the carbon reduction effect that we're either choosing to get or regulated to get. So we have the tools, we have the hardware, and we have the ability to put these systems together that allows our hydronic market as we go forward to keep up with what Tom was talking about. I mean, I was just amazed at the regulations that you were talking about and how quickly some of this stuff is happening. 10 years from now, think about, are you going to even be able to replace a gas-fired boiler? That sounds like a ridiculous question, probably, but given what's happening right now, I don't know if I'd treat it as a ridiculous question. So, folks, you need to look at alternatives. And I do think heat pumps, air-to-water, geo, they all have their place in our mix. And as I said this morning, our opportunity, I don't think, has ever been better. But we have to look at tailoring our systems to where not only the energy markets are going, the regulations, as also where buildings are going in terms of load. So don't give all the hydronic jobs away to the ductless mini-split guys. They'll take them. You know, and no offense, but we offer more than what they do, okay? So with that, I certainly want to thank Kalefi for sponsoring the keynote, and I want to thank HPAC for pulling off these conferences. I've mentioned to several people today, we have nothing like this in the U.S. I would love to see events like this in the U.S. that really bring together the practitioners that are going to push our market forward, and as well as the hardware. So my hat is off to you folks up here. And again, great to be back up in Canada. Thank you for your time. And I guess we go right into the Sweet Heat program next. So thank you.